Hi, Professor. This is Shuo. I'm going to talk about my assignment number 4. So the first problem is 4.19. I was given the data of ponderosa pine, and I was given the diameter and the volume of the tree. So what I'm going to do is express the y in terms of x. So here is the scatter plot of the diameter and the volume. So by the observation of the scatter plot, we can find the trend of the data appears to be increasing and concave up. So I'm going to apply the transformation ladder to linearize the data by changing our x to power to x. So and then I'm going to apply the square fit criteria on the transformed data to fit this model. And in this case, the value of k is determined by the equation 3.7 in the textbook. And then we have this equation. So next, I just calculate the value of the sum of the power of the x times y and the sum of the x power to the fourth. And then I substitute this value to the equation, and we can get the value of k. And then I plotting the transformed data. So we are expecting a straight line across the data and make the sample points as much as close as possible to the line. So and then so this line, so this plot looks good enough for our estimation. So we're gonna have the model looks like this, and then I plot the original data. We can see this is a curve across the data, and the point is close enough to the curve. So for the second problem is still the problem of the ponderosa tree, and but the data set is different. So the x value is the diameter of the tree, and y is the volume of the tree. And what we are going to do is fit the data by a 13th degree polynomial model. So first, so I applied the polyfit function in NumPy library for the fitting, and then we got this equation. So and then I plot the model. We got this plotting. So the size of the data is 14. So so we can say the 13th degree polynomial will pass through every point in the data set, and we can also figure that this disadvantage of the high order polynomial fitting is obvious. So we can see there are several oscillation of the polynomial near each end of the interval. So the change from decreasing to increasing will confuse us when we predict when we're doing prediction of the model. The next problem is the growth of East culture. So the T is the time, and the P is the population of the East. So so the scatter plot looks reasonable. The population is increasing by the time, but the trade of the data is not a straight line, so it's hard to determine the rate of the change. So I create a divided differences table by this function, and then we input the data, and we got this divided differences table. So and then I applied the low order cubic polynomial model. So the general form of the model looks like this. And then I'm gonna fitting this cubic polynomial to the data set. So first we need to select 4 points because we need because it's a 3-degree polynomial, so we need 4 points to let the polynomial pass through. So I select these 4 points from the data set, and then I apply the Lagrangian form of the polynomial. So then I substitute these 4 points into this equation, and we got the coefficient of the equation. So we plot the model of this cubic polynomial model is the green curve, and the red curve is the quadratic polynomial model, which was in the previous example. And then I'm going to compare the deviation of these two models. So the sum of absolute deviation of the cubic polynomial is 1,000 something, and the sum of absolute deviation for the quadratic polynomial model is less than 1,000. So the deviation of the quadratic model is less than the cubic polynomial model. So there is no doubt that the higher order polynomial model will lead to the least deviation for the given data set, because we're going to make every point pass through the polynomial in a higher order polynomial. But the lower order polynomial model presents while for the trade of the data in each interval we selected. So the next problem is the population of the United States from 1790 to 2000. So the X data is the time, which is year, and the Y is the population. So first we made this scatter plot, and from this plot we can see the trade of the data appears increasing and concave up, and there seems not outliers in this data set. And then I applied the divided differences table, and I used the function we made in the previous problem, and we got this divided differences table. And so by the observation of the table, we can assume that the first column, the first order column is constant. So we're going to apply the linear model as the lower order polynomial model in this problem. So, and then I applied the least square criterion for the linear system, and we got these two equations to determine the value of the coefficient A and B, which is the A is the slope of the straight line, and B is the intercept of the straight line. And then we got the result is looks like this, and then we have this model, and I plot this model. Looks like this, and it can present the trade of the data set, but it's not but it cannot present the change of the rate of the data, because in the straight line the change of rate keeps the same all the time. So my last problem is to write a system of equation to determine the coefficients of the natural cubic splines passing through the given data. So in order to determine the system of equation, we need some constraint. So the first constraint is we will make the spline pass through 2 data points, and so the first equation represents the spline 1, which is x1 pass through the first point, which is x1, y1. So we have this equation, and the same thing, we have the second equation represents the spline 2 pass through the second point, x2, y2, and then is the third equation represents the second spline pass through the second point, and the same thing, the fourth equation represents the second spline pass through the third point. So the next constraint we apply is because we require the smoothness of the spline system, so we need the adjacent first derivatives must match at the interior point, which is the x2, y2. So we take the first derivative of the 2 models on the point 2. So we have this equation. So the next strain is we need the adjacent second derivative must match at the interior point x2. So we take second derivative on model 1 and 2 on the interior point x2. So we have this equation. And the last constraint we apply is the derivatives at the exterior point, x1, y1, x3, y3, because there is no change in the first derivatives at exterior point. So the second derivatives of the exterior point must be 0. So we take the second derivative of the model 1 and model 2 at the first point and the third point. So we have this equation. So now we have 8 equations. So it is good enough to determine the 8 unknowns in the spline model, which is A1, B1, C1, D1, and A2, B2, C2, and D2. So for the first point we're given is this 3 points, and then we apply this 3 points in the equation we just derived, and then we can rewrite this equation set into a matrix, and then we solve this matrix. So the solution of this matrix is the coefficient of the model. So we got the first model. The model for the first data set looks like this, and then I plot in this model, and we can see the spline. There are 2 spines across 3 points, and the first spline pass through the first and the interior point, and the second pass through the interior and the third point. And then I just create a function to determine the coefficient of the equation system for the cubic spline. So the input ABC represents the X1, X2, X3, and the DEF represents the Y1, Y2, and Y3. And then I apply this to a list, and then we transfer this list to a matrix, and then solve the matrix, and then return to the solution. So and then I apply this function to our second data set, which is 310, 415, and 6 and 35. And then we got the coefficient of the model, and plotting the model looks like this. And then we then do the same thing for the third and the fourth data set. So we got the third and the fourth cubic model. That's pretty much about my assignment number 4. Thanks for review.